I'm going to talk about some perturbative studies of parafermions that is in some preliminary stage right now. So let's just come to the outline. And I'll first motivate by telling you what parafermions are and where we expect to find them. And expect because we have not quite yet found them, but we have some strong suspicions to believe that these are some exotic excitations that do exist in nature, and some experimental progress is still happening to find them. I'll go back to some Ising chain-like system, which we all know from our courses in StatMech and all, and think of it as a model for free fermions. And I'll use that to introduce the clock model, which we want to solve, which is a similar model for the Ising model. But it's not directly solvable, so instead I'll try and motivate solving this using something else called the Baxter Hamiltonian, and finally treat the clock model as a perturbation of the Baxter Hamiltonian. So this is the brief outline. So where are parafermions expected to be? Where do we expect to find them? Just the details are not important, but the schematic basically shows you a 2D substrate where some fraction quantum Hall systems are in contact with some superconducting phases and ferromagnetic phases in some substrate. And these red points, these interfaces are supposed to have some fractional excitations. These excitations are basically what give rise to parafermionic excitations. And this is where we expect to find them. We have not yet found them, but. And what are these excitations exactly? So these are basically simply understood as some set of identical particles on a 1D lattice with some Zn fractional statistics. By Zn fractional statistics, I simply mean that unlike bosons or fermions, instead of giving a plus minus 1 on exchange, they just give me some general nth root of unity. That's all parafermions are. And that's all the algebra we need to worry about. So let's go back to some model like the Ising spin chain that we have all probably seen. And instead of the usual chain where all the spin coupling, on-site spin couplings are set to some common magnetic field, external magnetic field H, and the spin interaction is set to J, I have kept all of them arbitrary to have the model in its full generality. And a simple Jordan-Wigner transformation on the Pauli matrices can give rise to these fermionic variables. They follow the standard fermionic Clifford algebra. So this is indeed a model of fermions. And it's a quadratic in fermions, and indeed it's solvable. In fact, its spectrum is that of what you'll expect from free fermions. By free, because you can think of the spectrum as coming from L states, each of which is either inhabited or not inhabited by a fermion. So it contributes with a plus minus, and this is the full spectrum. These are all the 2 to the power L states of the system, of eigenenergies of this Hamiltonian. And these epsilon i's are gotten from some sparse matrix F of some 2L dimensions. So there's a huge reduction in complexity from 2 to the 2L to L square. And this is what one means when they say that the Ising model is solvable. You can get it from this matrix F, all the eigenvalues and correlation lengths and all those things. So now let's move on to some Zn clock model, which is a similar model compared to the Ising change, but for parafermions this time. So these on-site matrices are, instead of Pauli matrices, now some generalized Zn matrices. The algebra is similar to that of parafermions, and these are some spin-spin terms. And doing a Jordan-Wigner transformation again, changing the variables, you can identify some parafermionic degrees of freedom, write this quadratic functional in parafermions, the Hamiltonian. But there's no analytical way of solving this model, at least so far. There's no way of solving this model for generic values of N and L. So there's no reduction in complexity for the system. And to get the spectrum, you'll have to try and diagonalize it numerically and fully. Notice that I've kept these Hermitian conjugate terms separately because this by itself is not Hermitian conjugate because of these roots of unity factors. But if I am being a little crude and naive, if I just drop these Hermitian conjugate terms, what we find is what is also termed as the Baxter Hamiltonian, because Baxter first wrote it in 1979 or something. And turns out that even though this model is not Hermitian, it's solvable. Its spectrum is exactly known, and its spectrum is exactly that of free parafermions. And free in the same sense as which Ising chain is represents a set of free fermions. You have some L sites, and you just need to pick these phases for the parafermionic states to be excited in. So in this model, there is indeed a reduction of the complexity from n to the 2L to L square again. But what can this be used for? So recall that in quantum mechanics, we almost always work with some Hermitian Hamiltonian systems, unless you are in the open quantum system business. And in perturbation theory, we just work with the unperturbed Hamiltonian, and we add on perturbations on top of that and study those perturbations in the coupling constant. So to borrow from these ideas, I'll just consider a general Hamiltonian as a function of lambda, as shown. And at lambda equals 0, this model is solvable. As I told you, there are some algebraic techniques you can use to solve this model exactly. And at lambda equal 1, it's the desired clock model system, which is not solvable, but it's Hermitian, so it's useful for quantum mechanics. So the key idea is to treat this thing as a perturbation and extrapolate to lambda equal 1 and see whether we can comment on the spectrum in at least some approximate manner, because the goal of perturbation theory is to be approximate, right? And before you think that this is all nonsense, and let me just say why it will make sense soon enough. But recall that in standard perturbation theory, we just take an ansatz for the spectrum. We have a we have a solvable part of the spectrum, and then we put an ansatz of a power series, like function in this case, the characteristic polynomial, the eigenvalue equation, and then solve term by term and truncate at some specific order, because lambda is small, so truncation is more or less valid in most cases. And typically you truncate at you can truncate at up to 1 by lambda order, but can this be done for lambda equal 1? The answer is, if you resum the series, it can still be done. So we have some resummation methods. These are standard in literature. In particular, Pade approximants work very well. And I'll just show you a result slide before I go to some technical aspects of this problem. So this is some n equal 4, L equal 2 system, which is exactly solvable. You can diagonalize it exactly. So you can compare the actual results with the approximate results. And these black curves are actually one of the E of lambdas, which will go to the ground state energy of the clock model. So as you notice, we can use these dotted lines are gotten from perturbation theory. This I'll explain what these P22 and P44 mean. But these dotted lines are gotten from perturbation theory, and these are two examples of n equal 4, L equal 2 systems for some randomly chosen couplings. But just to give you an idea that this works, at least for some E of lambda, this can be done, even though the value of lambda is order 1. So now what are Pade approximants, diagonal Pade approximants in this case? This is a small aside, not many details are important, but suppose you have a function with a formal power series expansion. The goal is to find some mth degree polynomials such that the ratio matches the first 2m coefficients of the Taylor series, and this whole thing is called the diagonal Pade approximant, and this defines the diagonal Pade approximant. And the most important properties for these approximants is that for a huge class of functions, these will converge to the actual value of the function, even when the Taylor series might be divergent. And this can be checked numerically for a large class of functions, or analytically proven also for a lot of functions. And our question is whether the same can be said for these E of lambdas that we want to calculate in our problem. And how does Pade really work, or when does it work rather? Is like, consider this simple function that we can all understand, like imagine in our heads, square root of 1 plus x. You can expand it about some x equals 0 point, get a Taylor series out of it. And we all know that the Taylor series is only convergent in the unit disk, right? So we know that the Taylor series will converge slowly. Slowly is not important, but nonetheless it converges slowly in this disk. But turns out that Pade approximants converge very rapidly in the full complex plane, albeit this small window on the negative real axis where the branch cut lies. So, and this is a schematic plot of the 10, 10 approximant. And even at x equal 100, it's quite a good approximation. So this is just to indicate that Pade approximants work even when Taylor series does not work. And Pade approximants are gotten from Taylor series. So I'll just quickly conclude as to how to exploit this behavior of Pade approximants in our problem. And this is the same plot I gave earlier for the n equals 1. And firstly, when will it not work? So Pade approximants are bound to fail. So as in this example, they don't work on the branch cut. If you try and evaluate it near the branch cut, they'll blow. So because the poles lie exactly on the branch cut. And so they'll not work when there's a branch point within this segment where we are doing the perturbation theory. So it's bound to fail there. And this will happen in our system because there are some E of lambda, as I showed in the Baxter Hamiltonian, which are complex at lambda equals 0. And they are going to be real at lambda equal 1 because they are the eigenvalues of a Hermitian system. So from the only way of going from complex to real in these sort of situations as a root of the polynomial equation is to encounter a branch point in between. So so this method will fail for those values. But this motivates us to look for, let's say, even values of n, where -1 is always a root of unity. So you have a state like state with energy like this in the Baxter system, and hope that this approximates the true ground state as well. So you start with the unperturbed energy eigenvalue as this, and build up the perturbation ansatz, and do a Pade analysis on this. And in low dimensional cases, as far as I can see so far, I've checked that at least numerically it works for a wide range of couplings. However, I don't yet have a proof for the full range of couplings so far, and that's in the work right now. And also to increase the dimension of the problem, and that's where I'll end. I'll have some more technical details after this, but I'll take questions rather.
You can ask your questions.
Why did you say you have to always encounter a branch cut?
So if you go back to this, so this thing, see, note that lambda equals 0 is the solvable model, but it's non-Hermitian. So its eigenvalues are complex. They are not all real. Some of them are definitely complex, as I showed in this slide. These omega are some roots of units. So a lot of these eigenvalues are complex. But at lambda equal 1, this is a Hermitian matrix. So we know that Hermitian matrices have real eigenvalues. So to go from a complex to a real eigenvalue continuously, you have to go through a branch point, roughly. You can think of that. So there'll be a branch point on between 0 and 1, left of which will be complex, right of which the eigenvalue will be real. Another way to think about is, see, you can write down, these are finite dimensional matrices. You can write down the characteristic polynomial, and the root of and E of lambdas are roots of those characteristic polynomials. So there will be some square root, cube roots, nth roots sitting in those equations as functions of lambda, and hence you have branch points. You have a lot of branch points in general. Whether they lie on between 0 and 1 is the question. And for these eigenvalues, which are complex, they'll definitely lie on the real axis, between 0 and 1 in fact. So for those, this technique is not very useful, so far at least. I don't know how to extract information from this technique for those eigenvalues. But for some ground state like systems, I can indeed. There are always some states for which you can comment. You can get the lambda equal 1 eigenvalue. Well, and so the key idea is to exploit this complexity thing. So because we are always in StatMech systems talking about thermodynamic limits and all, and this scales horribly. Order n to the 2L scales horribly with L. So the key idea is for larger systems, whether these numerics, whether we can develop an algorithm that will ease out the numerics for some of these eigenvalues, and then we can compare some results. Maybe if we have time.
Could you have started with the Hermitian conjugate first and then it solved that and then
so of course this is the full Hermitian system which I want to solve, but there's no known technique to solve it yet. So
what I'm asking is the Hermitian conjugate by itself solvable?
Yeah, its spectrum is exactly the same, but the states are different. Yeah.
Could you do this like it would be equivalent to do this process?
It'll be equivalent. And yeah, actually that's just a choice of basis for this tau and sigma, if you think about it.
Okay, thanks.
Yeah.
So since there are branch points there, so you did that analysis for ground state where all the eigenvalues are -1.
Yeah, so I took a special example n equal 4, so that yeah, exactly. So this thing is actually the ground state for n equal 4 system, where I can just work with all the negative ones, start with that, and then get the Taylor series, do a Pade analysis, and these are some P2 to P4, not very high order. These requires like first 5 terms, these require like first 9 terms. So it's not that high in order also. And I fit and exact function can also be solved because the characteristic polynomial is exactly so. You can find the roots of the characteristic polynomial. So you can compare with the black line. And so basically I can predict the ground state energy of the full clock model, even using Pade. So that's the advantage. Of course, this is a very low dimensional system where you could have just done the numerics directly. But the key idea, so in literature, there are some papers where you go till L equal 200 or something. Of course, those are very different techniques. But the key idea is to raise the value of L without raising the complexity too much.
So if you have any other questions, you can ask him later. Thank you, Kaustubh.